continue our discussions on the solution of the linear harmonic oscillator problem, solution corresponding to the linear harmonic oscillator problem. Once again, we will be solving the Schrodinger equation, and so this lecture will be again on obtaining the solution for the linear harmonic oscillator problem. And as I had mentioned before, the reference for this and even my earlier lectures is our book on by myself and Professor Lokanathan on quantum mechanics, theory and applications, and published by Macmillan India in India, and also by Kluwer in Netherlands, by Kluwer in Netherlands, and this is the 5th edition. So, that will be our reference. So, in my last lecture, we had discussed the solution of the confluent hypergeometric equation. Now, as we know that the confluent hypergeometric equation is x d2y by dx square plus small c minus x dy by dx minus a y of x. So, we tried to solve this equation by using the power series method. This method is also known as the Frobenius method, and this Frobenius method, in this method, Frobenius method, we assume a power series expansion of this, and usually it is written C, but since C appears here, so we will write d's of r x to the power of p plus r. When we substituted this equation, this solution in this equation, we found that p will be either 0 or 1 minus c. These are the roots of the indicial equation. These are the roots of the indicial equation. These are the roots of the indicial equation. Then we had also found that that dr over dr minus 1, that is dr was equal to p plus r minus 1 plus a divided by p plus r minus 1 plus c into p plus r times dr minus 1. So, the coefficient dr and dr minus 1 are related through this equation, and this equation was known as the recurrence relation. This equation is known as the recurrence relation. So, let me take p equal to 0 first, and so we have this is equal to r minus 1 plus a divided by r minus 1 plus c divided by r multiplied by dr minus 1. So, we calculated using this relation, we calculated d1 in terms of d0, d2 in terms of d1, and so on. So, if I assume, for example, that d0 is equal to 1, if I assume d0 is equal to 1, so I assume r equal to 1, so I get d1. If I put r equal to 1, so this becomes 1 minus 1 is 0. So, a by c into 1, d2 will become 2 will be a plus 1. So, a plus 1 divided by c plus 1 multiplied by 1 over 2 multiplied by d1 multiplied by d1. So, that is a into a plus 1 divided by c into c plus 1 into factorial 2 and so on. So, we get the solution p is 0, p is 0. So, therefore, for p equal to 0, this equation becomes dr x to the power of r. So, we will have d0 plus d1 x plus d2 x square plus so on. We are assuming d0 is equal to 1. So, this becomes 1 plus a by c x plus a into a plus 1 into c plus 1 x square by factorial 2, 1 into 2, and then it will be 2 factorial times 3. So, factorial 3. So, this is the infinite series. So, we obtain as one of the solution corresponding to p equal to 0, one of the solution as say y of x, the first solution y1 of x, this will be equal to 1 plus a by c into x by 1 factorial plus a into a plus 1 into c plus 1 x square by 2 factorial plus a into a plus 1 into a plus 2 divided by c into c plus 1 into c plus 2 x cube by factorial 3 plus so on. So, let me write this down, a into a plus 1 into a plus 2. This equation, this infinite series is usually denoted by f11 a comma c comma x, and this is known as the confluent hypergeometric function. Confluent hypergeometric function. It is an extremely important function, and I would like all of you to understand this very carefully. Now, let me consider the special case. I will consider the p is equal to 1 minus c also in a moment, but before that let me tell you an important property. Let me tell you an important property of this confluent hypergeometric function, and that is, let us take this simple case when a is equal to c. When a is equal to c, this factor is 1, this factor is 1, this factor is 1. So, f11 when a is equal to c, a x, this is equal to 1 plus x by factorial 1 plus x square by factorial 2 plus x cube by factorial 3 . I usually ask my students, what is the domain of convergence of this series? That means, for what values of x is this series convergent? If you would like to think for a moment, normally the students reply me back that this series is convergent for mod x less than 1. Now, that is not quite true. This series, as you know, is e to the power of x, and so therefore, this series is convergent for all values of x. in fact for all complex values of x. If you take x is equal to say 0.1, then it converges very rapidly. So, it will be 1 plus 0.1 plus 0.01 divided by 2, that is 0.005 or something like that, and so on. So, it converges very rapidly. For x is equal to 1, then what will happen is that first the numbers are large, but then it will come down. Even if you take a value, let us suppose x is equal to 10, then eventually the factorials take over. Initially the value of each term increases. First term will be 10, then this will be 100 divided by 2, this is 50, this is 1000 divided by 6, that is about 100 and something. So, even for a value x is equal to 10, it will take a very large number of terms, but this series will converge. And in fact, if you use your calculator, it will be a number which is very close to 22,000, 22,000 plus, 20,050 or something like that. So, that means even if you take a value of x is equal to 1 million, the value of the function e to the power of this x will be finite. It will be an extremely large number, but it will be finite. So, this series, this infinite series is convergent for all values of x, and you should write convergence for mod x less than infinity. All values of x, this series is convergent. However, the value of this series increases with x, so that the series is convergent, but the value of the function will increase. As I had told you that for x is equal to 10, the value becomes extremely large. I hope I have been able to convey you. So, this infinite series is convergent for all values of x. So, therefore, this is a valid solution of the confluent hypergeometric equation for all values of x, except for c not equal to 0, -1, -2, etc. Because for c equal to 0 or negative integer, this denominator will be 0, and therefore, the function will blow up. Now, let me look at the other solution. Now, I go back to my recurrence relation, which I had written down here, and I now assume p equal to 1 minus c. So, if I assume p equal to 1 minus c, then I will have dr is equal to, please see this equation will be equal to r minus 1 plus a minus c plus 1 and divided by r into r minus 1 minus 2 minus c. If you just do a little bit of algebra, this will come out, because if you put p is equal to 1 minus c, so this becomes 1 minus c, this becomes 1 minus c. So, 1 and 1 cancel out, c and c cancel out, and r comes out, and this comes out to be 1 minus c plus r. So, I write this as r minus 1 minus 2 minus 1 c. So, 1 minus c, 1 cancel out. So, this is a plus r minus c, and I write this down as a plus r minus c, and I have added and subtracted 1. So, I have just rewritten it slightly. The reason why I have rewritten in this form is because you can see now that if I compare this with this expression, I hope all of you can see this, A will be replaced by A minus C plus 1 and C will be replaced by 2 minus C. So, therefore, the second solution y2 of x will be therefore f11. For A, I must write A minus C plus 1. For C, I will write 2 minus C and x. So, therefore, the two independent solution of this equation, that is x d2y by dx square plus c minus x dy by dx minus a y of x is equal to 0. As I said, this is the confluent hypergeometric equation. So, we obtained p is equal to 0 and 1 minus c. These are the roots of the indicial equation, and the two solutions are. So, the two solutions are, so the general solution of this equation is C1 x to the power of 0 and then f11 a comma c comma x plus C2. You remember that we had summation the x dr x to the power of p plus r. So, if I take r here, so x to the power of p here. So, it will be x to the power of 1 minus c f11 a minus c plus 1 2 minus c comma x. So, this is the general solution. So, this is the general solution, because a second order differential equation will have two solutions. So, the general solution of equation 1 of the confluent hypergeometric equation is given by this. One more thing, we had seen that when c becomes 0 or negative integer, then this solution does not remain valid, it becomes infinite. And when c becomes a positive integer, then this quantity becomes a negative integer. So, therefore, this solution blows up when c becomes positive integer. So, the general solution of this equation, so I can write down that this is the general solution for c not equal to 0 plus minus 1 plus minus 2 is equal to 0. Actually, when c is equal to 1 plus 1, then this is a correct, this is all right. And when c is equal to, let us suppose, minus 3, then this is all right, but this is then not all right. I repeat that, let us suppose when c is equal to 2, then this function will be okay, because c appears in the denominator, but this function, this will be 0. So, this will not be a valid solution. Similarly, for c is equal to, let us suppose, minus 3, this function will blow up, but this function will not. So, one of the solutions will be all right. For the other solution, there are tricks to obtain that. This I have given in the appendix of the book that I had just now mentioned, but you can find it in any book on mathematical physics. A very good book on mathematical physics is by Irving and Molyneux. MULLIUNUX, Mathematics for Physics and Engineering. It is published by Academic Press. It is a very nicely written book and has lot of examples, and if you want to study, for example, the solution of second order differential equations, Bessel functions, Legendre functions, and other than that, this is a very good reference. Actually, in the problem that we will be considering, C will come out to be half. So, therefore, both of them will be valid solution. So, I have obtained the general solution of this equation. Now, why am I doing all this? My overall aim is to solve the Schrodinger equation. So, let me write down the Schrodinger equation. So, d2 psi, the time independent Schrodinger equation, d2 psi by dx square, mu is the mass of the particle, h cross is the Planck's constant, E minus V of x. But V of x for the harmonic oscillator is minus mu omega square x square psi of x is equal to 0. So, what I do, I think I had done this once before. Let me quickly, in order to write it in a convenient form, I write as xi is equal to gamma x. I had done this before. So, we get this equation, the above equation becomes d2 psi by d xi square plus 2 mu e by h crosses. This becomes gamma square times this. So, I put gamma square here minus mu square omega square, that is mu square omega square by h cross square xi square by gamma to the power of 4. So, I choose my gamma, I choose, which I have done before, I choose my gamma so that this is 1. So, I obtain and this I put as lambda. So, I choose my gamma so that this is equal to under root of mu omega by h cross, and so therefore, the Schrodinger equation becomes for the harmonic oscillator problem plus lambda capital lambda minus xi square, psi of xi is equal to 0. Now, what I do is that I now want to solve this equation. So, because there is a xi square term appearing here, let me make a transformation, that let me define eta is equal to xi square. I define eta is equal to xi square. So, if I do that, then I will obtain, please see this carefully, d psi by d xi is equal to, I want to express this in terms of the new variable eta, d psi by d eta times d eta by d xi. So, that is 2 xi. I differentiate this again, So, I get, let me write it in the next line, d2 psi by d xi square. So, I get d2 psi by d eta square plus multiplied by d eta by d xi, which is 2 xi. So, this becomes 4 xi square. Xi square is eta, 4 eta plus I differentiated with respect to xi. So, this is 1. So, 2 d psi by d eta. So, I substitute this in this equation. So, I get d2 psi by d eta square 4 eta plus 2 d psi by d eta plus lambda xi square is eta. So, eta psi of eta is equal to 0. So, using this as the independent variable, I define the variable eta is equal to xi square, and I make a simple transformation, and the above equation becomes something like this. So, I rewrite this. What I do is I divide by 4 eta. I divide by 4 eta. So, to obtain d2 psi by d eta square plus 1 over 2 eta plus lambda over 4 eta minus 1 by 4 psi of eta is 0. Everything till now is rigorously correct. There is no approximation that I have made anywhere. Sorry, 1 over 2 eta d psi by d eta. Sorry, I am sorry. This is psi prime. That is, this is psi prime is d psi by d eta. I missed that. Now, for large values of eta, that is for large values of xi square, this term will be very small. This term will be, because there is a eta which is coming in the denominator, this term will become very small. So, we will have just these two terms d2 psi by d eta square minus 1 by 4 psi of eta is equal to 0. And I know the solutions of this. Psi of eta will be e to the power of plus minus half eta. So, this suggests that we try out a solution psi of eta which is equal to y of eta e to the power of minus half eta. E to the power of plus half eta, that is plus half xi square, will blow up at xi is equal to infinity. So, we try out a solution like this. We try a solution like this. So, we write this equation 4 eta d2 psi by d eta square plus 2 d psi by d eta plus lambda minus eta psi of eta is equal to 0. And we solve this equation by assuming, because for large eta it is given by this. So, we substitute this solution in this equation. It is very straightforward. I differentiate it once, d psi by d eta will be equal to dy by d eta e to the power of minus half eta minus half y of eta e to the power of minus half eta. Then I differentiate it again, very straightforward derivation, d2 psi by d eta square. This is equal to d2 y by d eta square. I differentiate this again, e to the power of minus half eta. And then when I differentiate the second term, I will get minus half dy by d eta e to the power of minus half n. And here when I differentiate this term, I will get minus half. So, those two terms will be equal, as I am sure all of you would know. So, you will get dy by d eta e to the power of minus half eta, and then if I differentiate this term again, I will get minus half. So, plus 1 by 4 y of eta e to the power of minus half eta. Now, next what I do is that I substitute this here, this here, and this here. And as you will see, all the terms involve e to the power of minus half eta. So, that term e to the power of minus half eta, this term which appears in all the terms will just cancel out. This term will, when I substitute for d2 psi by d eta square, d psi by d eta and psi of eta in this equation, this term will be common to all of them and then it will cancel out. So, I obtain 4 eta, please see, d2y by d eta square minus dy by d eta plus 1 by 4 y of eta. This is the first term, this was this term, and then plus 2 d psi by d eta. So, plus 2 bracket dy by d eta minus 2 times this. So, therefore, minus y of eta, because 2 into minus half is minus 1, plus lambda minus eta y of eta. This is equal to 0. So, you can now see that, please see this, 4 eta times 1 by 4, that is 4 cancels out. This term is eta y of eta and there is a minus eta y of eta. So, these two terms cancel out. I hope you are able to understand. So, this term will cancel out with minus dy by d eta. So, we will obtain 4 eta, let me do it in carefully, d2y by d eta square plus 2 here minus 4 eta dy by d eta. So, this term is taken care of, this term is taken care of, this term is taken care of, plus lambda minus 1 y of eta equal to 0. What I do next is I divide by 4. I divide by 4 to obtain, if I divide by 4, then I will obtain eta d2y by d eta square plus 2 by 4 is half minus eta dy by d eta plus lambda minus 1 by 4 y of eta. So, the Schrodinger equation gets transformed to this equation, and let me now write down the confluent hypergeometric equation. The confluent hypergeometric equation, if you remember, x d2y by dx square plus c minus x dy by dx minus a y of x is equal to 0. So, this is my confluent hypergeometric equation. So, we find that we have actually obtained a confluent hypergeometric equation. So, c is equal to half and a is the minus of that. So, a is equal to 1 minus lambda by 4. So, since c is half, both the solutions, one solution was f11 a comma c comma x, this was one solution, and the other solution was, if you remember, x to the power of 1 minus c f 1 a minus c plus 1 comma 2 minus c comma x. Both solutions are convergent series, and they represent the most general solution of this equation, the complete solution of this equation. So, please see this, that I have here the complete solution is. So, let me write down what is a minus c plus 1, or first let me write down what is 2 minus c. 2 minus c is equal to 2 minus half. So, this is 3 by 2, and a minus c plus 1 is equal to, a is 1 minus lambda by 4 minus half plus 1. So, that is minus a half. So, this will be 3 minus lambda by 4, 3 minus lambda by 4. So, my two independent solutions are F11 a, that is 1 minus lambda by 4 comma c, that is half, and eta, which is actually xi square. This is one solution, and the other solution is x to the power of 1 minus c. C is half, 1 minus half is half. So, that is square root of x, square root of x, square root of eta, square root of eta F11 3 minus lambda by 4 into 3 by 2 into eta. And as you know, eta is equal to xi square, and xi we had said was equal to proportional to x. So, eta is actually gamma square x square. So, now you remember that we had assumed psi of eta was equal to y of eta e to the power of minus half eta, and eta is equal to xi square. So, the complete solution of the one dimensional Schrodinger equation for the free particle, for the linear harmonic, for the linear harmonic oscillator will be y of xi, please see this, some constant c F11 a, as we said. So, 1 minus lambda by 4 a, this is a, c is half xi square e to the power of minus half xi square plus c 2 square root of eta. Square root of eta is just xi F11 3 minus lambda by 4 comma 3 by 2 to xi square e to the power of minus half xi square. This is the complete solution, rigorously correct and valid for all values of xi. But there is a problem, and the problem is that you remember that we had said f11 a comma c comma x is equal to 1 plus a by c x plus a into a plus 1 into x square by factorial 2 plus a into a plus 1 into a plus 2 into c plus 1 into c plus 2 x cubed by factorial 3. If this series, understand this point carefully, if this series is allowed to go to infinity, that is, if this series remains an infinite series, then although the series is convergent, it will behave as e to the power of plus xi square, which is obvious because e to the power of plus x and x is xi square. Actually, I should write eta here, does not matter. This function behaves as e to the power of x. So, therefore, if this remains an infinite series, then it will behave as e to the power of xi square. So, the total function will behave as e to the power of plus half xi square, and so the wave function will blow up at infinity. And therefore, the wave function will not be normalizable. This can be averted if you make this a polynomial. If you make this, you can make this a polynomial only if a is a negative integer. So, for example, if a is equal to minus 1, then this term will be 0, this term will be 0, all the remaining terms will be 0. And only this term will survive, these two terms will survive. So, therefore, for this function, that is for f11 a comma c comma xi square multiplied by e to the power of minus, let me repeat what I have just now said. If this infinite series is not terminated, then it will behave as e to the power of xi square for large values of xi. And so, therefore, the function will, the product will behave as e to the power of half xi square. And so, therefore, the wave function will blow up at infinity. It will be a valid wave function, but it will not be a square integrable wave function, because the wave function will have a very large value at infinity. This can only be averted if this infinite series is made into a polynomial, and because there is a into a plus 1 into a plus 2, this can be made into a polynomial only if a is a negative integer, that is either 0 or 0. If it is 0, then 0, minus 1, minus 2, minus 3, etc. Only then you will have that. So, therefore, I have these two solutions. This series will become a polynomial if 1 minus lambda by 4 is a negative integer or 0, or this series will become 0, will become a polynomial if this coefficient becomes a negative integer or 0. So, let me summarize this, that is f11 a c x becomes a polynomial only when a is equal to 0, -1, -2, -3, etc., or equal to m minus m, where m is equal to 0, 1, 2, 3, etc. And now, what we have done is that y of xi, the solution, the actually psi of xi, I am sorry, psi of xi, the wave function was y into e to the power of minus half eta. Eta is xi square. So, psi of xi will be equal to y of xi, that is C1 f11 1 minus lambda by 4 in half, that is the value of c, into xi square into e to the power of minus half xi square. I will illustrate this in terms of examples. This is the general solution, square root of eta, that is square root of xi square. So, xi f11 3 minus lambda by 4 3 by 2. You have to remember this, these two formula you have to remember, then it will become very easy. I remember, so I think you can also remember. So, what we have found is this infinite series will become a polynomial only when this is a 1 minus lambda by 4 is equal to minus m. So, therefore, this is, if you take lambda on this, so this will be, if you multiply by both sides by minus 4, so minus 1 plus lambda is equal to 4m. So, you take 1 to this side. So, lambda is equal to 4m plus 1, which is m equal to 0, that means 1, 5, 9, etc. Then we see that this will become a polynomial when 3 minus lambda by 4 is a negative integer. So, you simplify that and you will get lambda is equal to 4m plus 3. So, this will be m equal to 0, 3, 7, 11, etc. These are the eigenvalues of the problem. These are the eigenvalues of the problem. And let me tell you that we had said that lambda is equal to 2e by h cross omega. So, this can take values 1, 5, 9, etc. And the first solution will be a polynomial solution, and this will be 3, 7. So, the solution will be an even polynomial, and this, as I will show you in a moment, 3, 7, 11, it will be an odd polynomial, the second solution. So, we will have an odd integer. So, therefore, 2e by h cross omega must be 2n plus 1. So, this implies E is equal to E n is equal to n plus half h cross omega. This is an extremely important result that we have been able to find out. These are the discrete energy eigenvalues of the harmonic oscillator problem. Now, let me go back. Now, let me go back that to our solution, to this solution, to the solution that we had written. Now, let me go back, and we assume that these are the two solutions. So, let me assume that lambda is 1. If lambda is 1, then psi, the general solution of the Schrodinger equation is psi of xi becomes C1 F1, this is 0 half xi square e to the power of minus half xi square, plus there can be another solution C2 xi F11 3 minus 1, that is 2 by 4, that is half 3 by 2 xi square into e to the power of minus xi square. Now, you see this here A is half, and as you know F11 is equal to 1 plus A by C x, sorry, here xi square, that is eta by factorial 1, A into A plus 1 into C plus 1 eta square by factorial 2. So, this will not become a polynomial, and therefore, we must choose C2 equal to 0. And therefore, this we should neglect. We should assume C2 equal to 0, because then this series will become a polynomial, and the first series will be equal to only A is 0. So, only a constant term will survive. So, for lambda is equal to 1, that is E is equal to half h cross omega, my psi of xi will be equal to C1 constant, that is 1 into e to the power of minus psi square. So, this is h0 of xi, h0 of xi is 1. So, this is the first eigenfunction of this solution. Now, in my next lecture, what I will do is, using these two equations, we will find out the eigenfunctions corresponding to different eigenvalues. Thank you.